All right, welcome to the final video where we talk about Lewis structures. Today we're going to be talking about polar bonds. A polar bond happens when there is two elements that are bonded together and one is more electronegative than the other. What happens is this electronegative atom pulls those electrons closer to itself, um, so it can feel that negative charge from the electrons more than the other atom. So in this case, the more electronegative atom attracts the electrons away and forms a slightly partial negative charge because it has those electrons closer. The less electronegative element will then have a slight positive charge. So let's just say if we had carbon and oxygen here, oxygen would pull those electrons a little bit closer. So if we imagine this is electron density in the bond, I'll give myself a different color here. Just make it red. More of the electrons would be over here towards the oxygen than they would be towards the carbon, because oxygen is more electronegative. What this causes is a slightly negative charge on this oxygen versus the carbon. When we are looking at how to identify if there is a polar bond, we need to look and see if there is a 0.4, greater than 0.4 electronegativity difference between these atoms. And this number is heavily discussed. It can be less or more, etc. But for our case in the class, we're going to say if it's greater than 0.4, it's going to be polar. Right. So if it's less than 0.4, it's not polar. So we're looking at 0.4 as the number. If it's greater than, it's going to be polar. If it's less than, non-polar. Okay, so if it's greater than 0.4, it's polar. Less than 0.4, it's non-polar. For this lesson, you will need this little sheet. Go ahead and copy just maybe the first couple rows here. You don't have to essentially write this entire thing. You just need like the Super 7 in the first two rows here, pretty much. There's one element that is not on here, that is hydrogen. Hydrogen's value for now is going to be 2.2. So make sure you write down 2.2 for hydrogen. You can pause the video and copy this if you need to. So we'll say hydrogen, 2.2 electronegativity value. Okay, we're going to go through these and say, are they polar or not? So is a carbon to hydrogen bond polar? So carbon is 2.5, hydrogen is 2.2. So is that difference greater than 0.4? It is not. So it's not polar. Carbon to nitrogen. So carbon's value is 2.5, nitrogen's is 3. So that is 0.5, so that is larger, so that is polar. Carbon to sulfur. What's sulfur's value? 2.5. So sulfur's 2.5, carbon's 2.5, so for this case, we'll say no. Carbon to oxygen. Oxygen is 3.5, carbon's 2.5, that is carbon's 2.5, fluorine's 4, that's polar. So identifying polar bonds by if it's greater than 0.4, it's polar, and if it's less than, it's nonpolar. And a carbon to hydrogen bond will always be nonpolar. Okay, so that's just identifying the bonds. Now we're going to apply that to the drawings that we've done. So we're going to talk about the difference between a polar molecule and a nonpolar molecule. So when we look at polar molecule, one end of the molecule is slightly more negative than the other in terms of electronegativity. So if we have an atom on one side that's more electronegative, it's going to make the molecule polar. It can be the same deal with a lone pair. The net dipole is going to be the sum of all dipole moments. So if there is a net dipole, you have a polar molecule. And when we talk about lone pairs, let's give them a value of 10 on the electronegativity scale when we compare them. So if we were going to look at all of these examples I have here, I'm just going to say, find the net dipole of this molecule. We're going to show the polar bonds. So the first thing we're going to do is we're going to draw it out. Little Lewis structure here. Methane's a great example. Then we're going to say, okay, are there any polar bonds? Is there a net dipole? Well, carbon's value is 2.5, and hydrogen's is 2.2. Is this polar? No, it's nonpolar. So in this case, there's no net dipole. It's not a polar molecule, so we just say nonpolar. as the answer, and that A looked kind of messed up. Okay, going over here, we have carbon, chlorine, 2 hydrogens, and another chlorine. So in this case, if it's drawn like this, we have to say, okay, what are the polar bonds? So carbon to chlorine is a polar bond, because if you look back at this, chlorine is 3.0, carbon is 2.5, so 3.0, carbon's 2.5. So that's greater than 0.4. So this is a polar bond. How we show polar bonds is we use an arrow with a little line through the back. So what you would do to show that this is a polar bond is I like to do it right on the bond as I draw that arrow right on there, like that. And that shows me that it is a polar bond. Okay? That little arrow. So that means it's polar bond. Now I have to ask myself, is there a net dipole? What is the net between these arrows? So if I have a vector going to the right at 3 and to the left at 3, what is our net gain? Well, our net is 0, right? Because it's not being pulled one way or the other. If you can imagine like the rope between these two chlorines, we get like a tug of war, right? So one of them has a value of 3, the other one has a value of 3. If they're both pulling at the same strength, nothing is really happening. So this does not have a net dipole. Because both of those are being canceled out, right? They're being canceled out. If this chlorine was in another spot, then it wouldn't be canceled out. So we'll see that. Let's just change this. That way we can talk about that. So let's move the chlorine to a different spot. So let's say this chlorine is here on the right. Now, from this one, we already know that both of these are polar bonds, right? So we have to say 3.0, 3.0. And our question is going to ask us to identify if it is a polar molecule and if there is a net dipole. Where is the net dipole? So the net dipole is just the summation of the two arrows. So sum of all dipole moments, the dipole moment is the arrow. What you're going to do is say, well, what's the average between those two? If I'm going up at 3 and I'm going to the right at 3, what is the average between that? Well, it's going to be a 45-degree line here, right? So our net dipole is going to be like that. 45 degrees up and to the right. So this is our net dipole right there. That would be a good enough answer. And I'm off the page a little bit. Let me move that over. I wasn't looking. So we have the up and the right. What's the average between that? 45 degrees, right? So what I'd expect you to do for this is draw the individual polar bonds and then have a net dipole facing the average way that is. It doesn't have to be too serious here, just so that we know, hey, it's that way. That's our net dipole. So our polarity of this molecule is going to be towards that way. Okay. So we're just basically saying, are the bonds polar, yes or no, drawing an arrow, and then moving from there. I just thought of a good one that we can do next that I don't have on there, so we're going to do this. CH2 FCl. So for this one, we would have carbon. Let's just say we have H's, we have fluorine, and then on the bottom we have chlorine. Okay. So for this, we know both of the hydrogens, that's not polar. We know that fluorine has a value of 4.0, chlorine has a value of 3.0. So we have a polar bond going this way and a polar bond going that way. What is our net dipole? Well, if we look at it in terms of like an axis on a grid here, we would have an upwards pole at 4 and a downwards pole at 3. What is our average? Well, our average is going to be an upwards pole at 1.0, right? So our net for this is going to be up, right? So you see how we find the net of that? 4 minus 3 is 1. So our average of that molecule is going up, okay? And then we need to do these two examples for lone pairs. So this is ammonia, and we would have it being drawn like this. Nitrogen to hydrogen. would be considered polar bonds, right? Because nitrogen is 3.0, hydrogen's 2.2. So we would have all of them pointing towards the middle, but the lone pair is 10. So there is a huge dipole facing that way. So all of these arrows are pointing towards the lone pair, right? It's pointing that way. So whichever direction you have the lone pair pointed to, that's where it's going. When we do water, you have to make sure that you draw it according to its Vesper geometry. It would look like this. The oxygen to hydrogen would be polar, so it would be pointing in a little. But what matters more is the lone pairs, right? We have going up to the right, up to the left. What's the net dipole? Straight up. Okay, so use the sheet. So use this sheet to figure out if bonds are polar or not. And then you're just looking at the number and saying, okay, what's the larger number? Go in that direction. If they're completely opposite from each other, like we have up here, they even out. If they're opposite of each other but have different numbers, whatever the larger number is, we're going that way. And then if there's lone pairs, it's most likely always going to be pointing towards the lone pair.